6.5 inequalities in one triangle. Our essential question, actually I have two for you. So here we go. How are the sides related to the angles of a triangle? That's the first one. And then the second one, how are any two sides of a triangle related to the third side? All right, the triangle longer side theorem. This is on page 337. And basically what this says is that in a triangle, the angle opposite the largest side is the largest angle. Which, if you think about it, the angle opposite the largest side has to be the widest angle, right? Because it's encompassing the largest side. And the angle opposite the smallest side is the what? Hopefully you guys know this. Is the smallest angle. Which makes total sense, I think. All right, before I move on to the larger angle theorem, I think I'll go ahead and draw a picture. So head on down to example 2 here, relating side length and angle measure. It says to draw an obtuse scaling triangle. You're going to mark the largest angle and the largest side in one color, and then the smallest side and the smallest angle in another color. So let's find my ruler. And 2 colors. So obtuse scaling means that I've got one obtuse angle and none of the sides are the same measure. So I'll make this angle obtuse. How about I'll label it? So how about we'll make this triangle ABC. So angle A is my largest angle. So I'll go ahead and mark the largest angle with orange. So that's the largest angle. And where do you think the largest side is? Well, just from my drawing, it's really obvious that it's opposite that largest angle, which makes total sense because this angle is wide, right? It needs this larger side to be long enough to connect the two rays that are forming angle A. Or I should say the two segments. All right, so then my longest side, or my largest side, is over here. It's BC. Maybe I'll make a key. So I'm going to go orange. These are the largest. And that's basically what this triangle longer side theorem said. The angle opposite the largest side is the largest angle. Makes total sense. Okay, and the angle opposite the smallest side is the smallest angle. All right, well, let's see. Where's my smallest side? Here's my smallest side, so which one's my smallest angle? B. How about I'll use yellow for that? So my smallest side and my smallest angle are opposite each other as well. Oh, and I better add my key. So the yellow is going to be the smallest. Okay, so back up, now that I've kind of explained the triangle longer side theorem, the triangle larger angle theorem is basically just the converse of this. So instead of saying the angle opposite the largest side, we're going to say the side opposite the largest angle. And then we'll do the same with the smallest stuff. So for this one, in a triangle, the side opposite the largest angle is the largest side, and the side opposite the smallest angle is the smallest side. Okay, so these are both basically saying the exact same thing, just do we put the angle first or do we put the side first? Either way, if you know that one angle is the largest angle, it's opposite the largest side, or if you know that one side is the largest side, then it's opposite the largest angle. And the same is true with the smallest sides and angles. Okay, moving on. Let's order angle measures of a triangle. So we're going to list the angles of triangle ABC in order from smallest to largest. Well, we know that the largest side is 13. So what's my largest angle? It's the side, or it's the angle that's opposite that, right? Because these rays here, or segments, have to encompass this larger side, so that makes this angle the largest. All right, now, but we were supposed to go from smallest to largest, so let me start with the smallest. So which angle is my smallest one? Well, my smallest side is over here. It's BC. So my smallest angle is going to obviously be right across from it. So angle A is the smallest. Okay, so the middle, right, not the largest, but the next one is going to be angle B because it's opposite the 12. And then again, the largest is angle C. So this goes angle A, angle B, angle C. All right. Now we'll order the side length. So instead of being given the sides and figuring out which angles are the biggest, now we'll be given the angles and we'll have to figure out which sides are the shortest or the longest. Well, it might be helpful if I figure out what this other side is, or this other angle is to begin with. So I know that all the angles in a triangle add up to 180. Let's see, these two triangles together add up to 120. So if they all add up to 180, what's this one going to be? Well, this one's going to be 60 degrees. All right, so my smallest angle is going to be across from my smallest side. And you want to actually look at the angle measures. You don't just want to look, I mean, to me, this triangle looks like an equilateral triangle, right? And it makes sense because they're all these angle measures are relatively close together. But we know for a fact that the smallest side is segment BC because it is opposite the smallest angle. Okay, the next one is going to be, well, 60 degrees is like the middle angle, right? Mid-size angle. And so it's opposite segment AB. And the largest angle is opposite the largest side. So the largest side has to be segment AC. And the order of these does not matter. You could have called this like segment CB, segment BA, segment CA. Okay, so hopefully you're finding that pretty easy. It's important that you understand these things, okay? All right, so triangle inequality theorem, that one's on page 339. So this talks about how the lengths of any two sides are related to a third side. So the sum of the lengths of any two sides of a triangle is greater than the third side. And this becomes super important when you get to trigonometry and pre-calculus, and even algebra 2 actually. This is really used to determine if a triangle can even be formed. Okay, so we use this. Because, for example, if I add up the lengths of two of sides of a triangle and they're not greater than the third side, then the third side can't, it's not going to be closed, so you're not going to have a triangle. Okay, so if I gave you, let me go ahead and draw just some random triangle here. Oh, okay, there we go. That would have been an example where it wouldn't have worked. All right, so if I give you this triangle with sides A, B, and C, then I know that the sum of any two sides, A plus B, has to be greater than C, or A plus C has to be greater than B, or B plus C has to be greater than side A. I think that was every combination there. And if it's not, if these are not the case, then you don't have a triangle. And I don't know if you guys remember, but when we did different triangle congruence theorems, such as side angle side, or angle angle side, or side side side, there was one that we said would not be an indicator to tell if two triangles are congruent. And that one was angle side side. This is an example of sometimes a triangle cannot be formed if you've been given this information. And a way to double check that a triangle can even be formed would be to create these inequalities using that triangle inequality theorem. Okay, so sometimes we don't even get a triangle when we're just given angle side side. Okay, and that's why, having just an angle is not enough information. One angle and two sides is not enough information. If you have all three sides, you can go through and you can double check that a triangle is even formed. We'll get to this again when we get to trig. Okay, but that's a bad one. Okay. All right, we're going to find some possible side lengths. So a triangle has one side length of 6 and another side length of 15. Describe the possible lengths of a third side. Okay. So I'm going to draw a couple triangles here. They're going to be the same. So I'm going to try and draw them exactly the same. I'm going to do one here, and then I'm going to do another one over here. Trying to make it look the same. Close enough. Okay, so these are the same triangles. All right, so we've got one side of 6. I'll make that the smallest side. Or actually, I'll make that the middle side. And the other side, 15. Okay, so if I'm looking for the smallest side here, then I know that, x plus 6 has to be greater than 15. Right? So my two smaller sides are going to have to be greater than my larger side. Okay, so this will give me a range for what my smallest side could be. If I solve this, and you solve these just like you do equations, right? You imagine that that inequality sign is just an equal sign. The only challenge is if you divide or multiply by a negative, you have to flip this sign. We're not going to do that though. So I'm not going to have any negatives here. So I just have x, let's see, the 6's go away, is greater than 9. So I know that my smallest side here can be any number greater than 9, any length greater than 9. Okay, so this is me finding my smallest side. Smallest possible side. I'll just put smallest side. Well, let's do that again, and let's get a range for what the longest side could potentially be. Okay, so maybe this time I won't know my longest side. That would make then 6 be my smallest side and 15 be my middle side. So this is me finding my longest side, or a range of values that could be my longest side. Okay, so what I'm going to do here is I'm going to take my two sides that are not my largest side, and I'm going to say, well, if I add those up together, they better be greater than my largest side. So basically, 21 must be larger than my largest side. Or in other words, I could rewrite this so that x is less than 21. That's what that really means. X is less than 21. So my largest side has to be less than 21. So that tells me then, I'm going to use a little number line here to kind of show you what I'm talking about. The smallest that my side could be, my third side of this triangle could be, is 9. And the largest it could be is up to 21. So this tells me I'm somewhere in between these two, right? I'm somewhere between from 9 to 21. Okay, so I can write a compound inequality that describes this region, right? The side that I'm missing, the third side of this triangle, is going to be somewhere in between. So it's going to be greater than, right, the smallest side, smallest possible length. And it's going to be less than the largest possible length, or the longest side. So my third side, the length of that third side could be anywhere between 9 and 21. So there's your final answer. And this is how I would suggest you do this. Set it up so that you have two separate triangles, right? They're the same triangle, but not. So your smallest side in your first triangle, that's what you're looking for. So you take your other two sides and you place them accordingly. Longest side goes with the longest side. Then you do the longest side search, where you use those two sides to be like your smallest and your middle side, and do another inequality. And then the values that you get for those two inequalities, that's where that third side is going to be in between, somewhere between 9 and 21. Now again, for inequalities, maybe I'll do a quick little review here on the side. So for actually, let's do it down here. Just a quick inequality review. So you solve them just like an equation. The only difference is that you have to flip the inequality sign if you multiply by a negative or divide by a negative. So solve like an equation. But flip inequality. if you multiply or divide by a negative. So for example, if I gave you negative 3x is greater than 24. Well, if I solve this, I'm going to divide both sides by a negative. So that means that you're going to have to flip this sign, right? You're going to flip that. But you solve just like you would any other equation. And that's because what's happened here is you've changed the values of each side. This side used to have all negatives, this side was all positives, and now you've changed it, so this side's positive, this side's negative. So it's going to change the value that goes in here. It's going to change the composition of this inequality. Okay. Is it possible for a triangle to have side lengths 3, 4, and 10? Well, we better double check this using that triangle inequality theorem. We know that in order for a triangle to exist, the sum of any two sides has to be greater than the third side. So, if I take the first two sides, and I say, hey, well, those two must be greater than 10. Well, is that true? That doesn't work. So right there, I could just be done. But I have to do this for every combination, just in case. So let's say that the first two sides I added and it was greater than the third. Well, then I'd keep working this out. So now I'll take, how about the first and the last two sides? Is that greater than the middle side? That is. How about now I'll do the last two sides? Is that greater than the first side? It is. Okay, so the other two combinations check out, but the first combination of sides that I did, these two sides, the sum of them were not greater than the third side. So this would be a no. In order for the triangle to exist, every combination of the sides, the sum of any two of those sides has to be greater than the third.